Hello, and welcome to Linear Algebra. This is lecture 36 on computing determinants. Last time, we talked about existence and uniqueness of determinants. So what we showed is that there is one and only one function, dn, from matrices of size n by n with entries in a field, valued in the field, that is alternating, multilinear, and normalized so that its value on the identity matrix is equal to 1. Right? So remember, alternating means that if you have a matrix with two columns equal to each other, then this function vanishes on that matrix. Another way of saying the same thing is that if you have two matrices and they only differ in that two of the columns are in the opposite order, then this function just changes sign. Multilinear means that if you view this as a function of the columns of a matrix, then fixing all of the columns save one, and this function is linear in that remaining column. And the normalization is precisely this, that it's equal to 1 on the identity matrix. This time we want to talk about some properties of the determinant. And in particular, we want to have various ways of computing it. Now, in our proof of existence and uniqueness, we gave one way of computing it inductively. This is known, let's give it a name now, this is the Laplace expansion, named after Pierre Simon Laplace, of the determinant along a row. Right, so for any I between 1 and n, the determinant of matrix A is equal to the sum, j goes from 1 to n, of minus 1 to the I plus j, little aij, determinant of capital Aij. Okay, so remember here, capital Aij is the matrix of size n minus 1 that you get by deleting from capital A the ith row in the jth column. Okay, so what we did last time was we fixed an I, and then we showed that this function satisfied all of the properties of the determinant function. Since we've shown that there is only one determinant function, then that means that it doesn't matter which I you choose, you get the same number, and that number is the determinant of A. Okay, so this is one way we have of computing the determinant. Here's a very nice consequence. If A is upper triangular, then the determinant of A is just the product of the elements on the diagonal. Okay, great. So let's prove this. As usual, we'll prove this by induction on n. So it's clear if n is equal to 1. If n is equal to 1, the matrix is of size 1 by 1, so it has a single element, and the determinant is that element. So this is clear in that case. Assuming it's true, for upper triangular matrices of size n minus 1 by n minus 1, we can expand along the last row of A, right? So we'll just take the Laplace expansion where we use the last row of A, which is mostly 0, right? So we get the determinant of A is equal to the sum j goes from 1 to n of minus 1. And here I'm going to take I equal to n. So I'll have A and j, and then the determinant of capital A and j. Right now, because all of these are equal to 0 except for the last one, I end up with minus 1 to the n plus n, A and n, determinant of capital A and n. Right? But now we use the inductive hypothesis because capital A and n is an upper triangular matrix of size n minus 1 times n minus 1. So altogether, we end up with A and n times the determinant of that matrix, which is A1, the product of diagonal entries of that matrix. And that gives us exactly the formula we wanted. Okay. Very good. So now you can say, well, that's fine for upper triangular. What about lower triangular? Well, of course, the same formula holds. And here's one way of establishing that. And establishing another nice property of the determinant at the same time. Namely, the determinant of a matrix is equal to the determinant of its transpose. Okay, so here's how we're going to prove this. Consider the function, call it E, that takes an n by n matrix, gives you back an element of the field. So what it is just going to be the determinant of the transpose. Okay, so I want to show that this function is equal to the determinant. And since we have an existence and uniqueness result, I'm going to show that it is a determinant function and hence equal to the determinant. Right, so we'll show by induction that E is a determinant function. So by uniqueness, the determinant function. Right, so remember, a determinant function just means that it is alternating, multilinear, and normalized. Okay, so for n equal to 1, A is equal to A transpose. So this is clear. Okay, so now let's check inductively. So first, let's start with multilinear. Let's check that E is multilinear. So let's say that you have a matrix A whose columns are the vectors alpha 1 through alpha n. And suppose that one of those columns, alpha k, is equal to a linear combination of beta and gamma. So here, beta and gamma are vectors, and E is a scalar. Okay, so E of A, by definition, would be the determinant of A transpose. Okay, so I'm going to use the Laplace expansion. I don't care which. No, I do care. I'm going to use the I equal to k. So here I'll have k plus j. And then here I would have akj but because I'm taking the transpose, I have a jk. And then I would have determinant of the matrix you get from the transpose by deleting the kth row and the jth column. Right, okay, so what is that? Well, so I have the sum, j goes from 1 to n, minus 1 to the k plus j. So this ajk, I can write as bjk plus e times gjk, right, where there's no jk. So where bj is the jth entry of the vector beta, and gj is the jth entry of the vector gamma. And then this is equal to the sum, j goes from 1 to n of minus 1 to the k plus j, bj, determinant of a transpose kj, plus e times the sum, j goes from 1 to n of minus 1 to the k plus j, gj, determinant of a transpose kj. Right, and then notice that this is equal to what you get from applying E to the matrix with columns alpha 1 through alpha k minus 1, followed by beta, and then alpha k plus 1 through alpha n, and then plus E times capital E applied to the matrix with columns alpha 1 through alpha k minus 1, followed by gamma, followed by alpha k plus 1 through alpha n. Right, which is exactly what we wanted to show to get multilinearity. It's easy to see that E is normalized because E of the identity would be the determinant of the identity transpose, which is equal to the determinant of the identity, which is equal to 1. So that just leaves for us to check that E is alternating. Okay, so let's check the case n equal to 2 separately from the others. If n is equal to 2, so alternating, I need to check that if you have 2 equal columns, then you get 0. So here, this would be. So if this column is equal to this column, I need to check you get 0. By definition of capital E, that's the determinant of the transpose, so that would be this. And we can just compute that. That's AC minus AC. That is indeed equal to 0. So for n equal to 2, it works. If n is at least 3, so let's say that column alpha k is equal to alpha L, and pick an I that's not k and it's not L. That's why I want n equal to at least 3. So now we're going to do the Laplace expansion along I. So we have E of A is determinant of a transpose. So this would be the sum, j goes from 1 to n of minus 1 to I plus j, A ji, because it's the transpose matrix, and then determinant of a transpose capital lower ij. And that's equal to the sum, j goes from 1 to n of -1 to the I plus j, a j I, determinant of a j, capital A j I transpose. Right, so if you delete the ith row and jth column from the transpose matrix, that's the same as deleting the jth row, ith column of A and then taking the transpose. And then we can write that as the sum, j goes from 1 to n of -1 to the I plus j, a j I, determinant of a j I, because by induction we know that the determinant of the transpose is equal to the determinant of the matrix, and then this is equal to 0 because we have the determinant of a matrix with two equal columns. Hence, by uniqueness, this function is equal to the determinant of A, and that's what we wanted to show. Okay, so wonderful. So having shown that the determinant of the matrix is equal to the determinant of its transpose, we now have a formula for the determinant of lower triangular matrices as well as upper triangular. And we also know that properties that we had before for columns are also true for rows. So let's say it follows that the determinant is also an alternating multilinear function of the rows of a matrix. Also, instead of expanding along the rows, we can expand along columns. So we have a Laplace expansion along columns. Right, so this says for any j, the determinant of A is equal to the sum, I goes from 1 to n, of -1 to the I plus j, aij, determinant aij. Right, so this is indeed what we ended up with right here. Of course, here we then used that that these were 0, but in general they won't be 0, and they give you a formula for the determinant. Okay, so we have Laplace expansion along rows. We also have Laplace expansion along columns. Another consequence is that we can compute the determinant using row operations. Right? And this is an efficient way of computing the determinant. So here's how you would compute it. Given a matrix of size n by n, coefficients in the field F, you can use row operations R1 and R3 to convert A into an upper triangular matrix B. Right, so remember R1, you're adding a multiple of one row to another one, and R3, you are switching the order of two rows. Let K be the number of times 2 rows were switched, then the determinant of A is minus 1 to the k times the elements on the diagonal of the matrix B, right? And that's how you want to compute a determinant in practice, especially if you're given a large matrix and you want to compute the determinant. This is what you want to do. Okay, however, for some purposes, especially when you're trying to prove properties, it can be very useful to have an explicit formula for the determinant of a matrix. So let's talk about that now. We actually used it sort of last time when we wanted to see that that a determinant function, so something is alternating in multilinear, that vanishes on the identity had to be identically 0. We did something very similar to what we're going to do now. So let's start by defining permutations. A permutation of the set of numbers from 1 to n is a bijection of this set. So sigma from this set to itself, a bijection. So another way of saying that is that if you look at the list sigma 1 through sigma n, this is the same as the list 1 through n as sets, but possibly in a different order. The set of all permutations of the numbers from 1 to n is denoted S sub n. And there's an obvious permutation, the identity. The identity permutation is denoted I. Okay. Every permutation can be represented by a matrix. Which maybe we would call A sub sigma, right, of size n by n elements in the field. So the entries of A sigma, right, Aij, would be equal to 1 if j is equal to sigma of I and 0 otherwise. Right, so just by looking at the matrix A, you can see what the permutation was. So for example, let's say that you give me sigma in S4, so this is permuting the numbers 1, 2, 3, 4. And let's say that this one is sigma of 1 is equal to 2, sigma of 2 is equal to 1, sigma of 3 is equal to 4, sigma of 4 is equal to 3, right? So I just have the same numbers, 1, 2, 3, 4, in some order. So here, the matrix A sigma would be a 4 by 4 matrix. And so for example, here, here, let me finish writing it and then I'll point out what it's doing. right? So aij is going to be 1 if j is equal to sigma of I, right? So since sigma of 1 is equal to 2, then I know that I'm going to get a 1 when I have j equal to 2 and I equal to 1, right? So a12 is equal to 1. And so this first row is telling me what sigma of 1 is, right? Sigma of 1 is equal to 2. The second row is telling me what sigma of 2 is. That's why I have something in the first entry. The third row is telling me sigma of 3 is 4, and the fourth row is telling me sigma of 4 is 3. Okay, now define the sign of a permutation to be the determinant of the associated matrix. Okay? So this is either -1 or +1. Right? Why? Because the matrix A sigma is just obtained from the identity matrix by putting the columns in a different order. So you can use column swaps to get to the identity. Every column swap changes the determinant by a sign. So you're going to end up with either a +1 or a -1. This sign satisfies two nice properties. Sign of a permutation is equal to sign of the inverse permutation, right? It makes sense to talk about the inverse because a permutation is just a function from the set 1 through n to the set 1 through n, right? So it makes perfectly good sense to talk about the inverse of that function. And because this is a bijection, it has an inverse, and the inverse is also a bijection, so a permutation. Also, the sign of a composition, right? So again, because these are just functions, it makes sense to compose them. The sign of composition is equal to the product of the signs of the individual permutations. Okay, so here is an explicit formula for the determinant of a matrix, and a really terrible way to compute the determinant of a matrix as soon as n gets large. Okay, so this is how you go from the individual entries of the matrix to computing the determinant. And I'll emphasize again that this is really useful if you're trying to prove theoretical properties of the determinant. But if you're trying to compute the determinant of a given matrix, unless that matrix has a bunch of zeros, this is a terrible, terrible way to compute it. Okay, but let's prove that this formula is true. Well, using multilinearity, what we can do is write the determinant of A where what we're going to do is look at each column and write it as a linear combination of the standard basis. Here, maybe it'll be clearer. We do that first. So let's say that A has columns alpha 1 through alpha n. And let's write alpha j as the sum of A ij I sub j of E I sub j. So here the index I sub j It's going to go from 1 to n. Okay, hopefully this is not too confusing. So instead of having I go from 1 to n, because I'm going to have a different dummy variable for each j, I'm going to denote it as I sub j. Okay, so here I have I sub 1 going from 1 to n. And so on. In the last one, I would have some I sub n going from 1 to n. A-I-N, n, E, I, n. Okay, so it's the determinant of this. So using multilinearity, we can write this as the sum. So here you'd have I sub 1 going from 1 to n, and so you'd have n of these capital sigmas. And then you'd have AI1, 1, product AI, n, n, and all of that multiplying the determinant, where now I have as first column EI1 up through EIN. Okay, so that's just using multilinearity. We can write the determinant of a matrix as a linear combination of the determinants of matrices where the columns are only elements of the standard basis. Now, since the determinant is alternating, this sum can be taken over distinct indices, right? So this determinant is going to vanish anytime there's a repetition among these columns, right? So I could restrict this sum so that I'm not summing over all possible indices, each one going between 1 and n, but only over distinct indices. So I have to have no repetitions, right? Well, that's the same as saying that you're summing only over permutations. So that means that the determinant of A would be equal to a sum where sigma varies among the permutations of A sigma 1, 1 up through A sigma n, n. And that gets multiplied by the determinant of E of the matrix whose columns are E sigma 1 through E sigma n. Right? Moreover, the ijth entry of this matrix, where you have E sigma 1 through E sigma n, is 1 if I is equal to sigma j, 0 otherwise. Right? That is, this matrix is a sigma inverse. So its determinant is sine of sigma inverse, which is the same as sine of sigma. Oh, thus we get the formula we want. Okay. And we'll stop there and pick it up from there next time.